Hello everyone, I am Hitarth and this is a joint work with Mahdi, Arash and Professor Massoud Pedram at USC, and our work is called Espresso-GPU, Blazingly Fast Two-Level Logic Minimization. We start with the motivating example that necessitated us to create Espresso-GPU. Now, neural net is a newly developed technique of representing layers of a neural network as Boolean functions. Applying standard quantization techniques on the outputs of neurons, we get a sparse Boolean function where different inputs are the minterms of the function. We can then apply two-level logic minimization techniques like the Espresso algorithm to obtain a compressed representation of the function. However, the problem is that the sparse function we get has hundreds of input variables and hundreds of thousands of minterms. Espresso algorithm's CPU's implementation takes hours to optimize even a single Boolean function, and hence it becomes essential to make Espresso algorithm more time efficient. Now let's go through some definitions to make things precise. So small f is a function that takes Boolean inputs and outputs are in 0, 1, and 2. For each output variable, its onset is the set of all inputs such that the function value for that input is 1. The offset and the don't care set are defined similarly. Now the cover capital F of a function is a set of cubes that contains every minterm of the onset. Similarly, the cover of the offset and the DC set are defined as R and D respectively. Now, the goal of Espresso is to find a minimal cover of the function. For that, it employs these 7 steps where steps 2 to 5 are applied repeatedly. Note that the steps of irredundant and reduce require the DC set as well, which is infeasible to compute for sparse function with hundreds of variables. Moreover, in our experiments of neural net, we also observed that the expand step compressed the function by a factor of hundreds, and the other steps only help marginally. And hence, we focus on the expand step, which converts a given cover of the function to a prime cover. Now let's try to gain a high-level understanding of how expand works. It takes the cover of the onset f and the cover of the offset r as the input. Now, in every iteration of loop of 1, it transforms an uncovered cube into a prime implicant. It does so by dropping a set of literals iteratively in loop 2. Now the question is, how does it choose the set of literals to be dropped in a single iteration? For that, it uses a one-step look-ahead heuristic to select a cube P star, and the current cube C plus is expanded to minimally cover P star. The selected P star has two properties. First is that C plus can cover P star without intersecting the offset, and secondly, C plus covers the highest number of uncovered cubes after the expansion of C plus to cover P star. Selecting P star is done by the computations in loop 3.1, 4.1, followed by 3.2 and 4.2. Here, we try to focus on the computations themselves rather than why these computations are needed. Having said that, we make the following observations. The algorithm uses a function called feasibly covered, which checks whether a cube C can be expanded to cover the another cube P without intersecting the offset. For this, it needs to calculate the distance between the expanded version of C and every cube of the offset. Another salient feature is that the cubes are assigned flags and the set of cubes are distilled whenever possible so that we only do the computations on the cubes which are relevant for that computation. For instance, we only iterate on active cubes in loop 3.1 and on feasible cubes in loop 3.2. Now, let's try to understand the parallelization strategy. So should we parallelize loop 1 so that multiple cubes are made prime in parallel? The answer is no, and there are 3 reasons behind it. First is that it increases wasteful computation because some of the cubes being expanded parallelly can try to cover each other. Secondly, the number of prime implicants may increase because same cubes of f will be attempted to be covered multiple times. Lastly, we also need independent copies of f and r since they are modified inside loop 2. So then how about loop 2? In loop 2, the expansion in the current iteration depends on the state of cubes from the previous iteration, and hence it is inherently sequential. And hence, we choose to parallelize all operations that happen in a given iteration of loop 2. Now let's understand the architecture of a GPU. GPU consists of a series of multiprocessors where each MP has again many processors. Different processors of a MP execute same instruction in a single clock cycle on different data. Then there is also a memory hierarchy of registers, shared memory, and global memory, with the access times increasing in that order. Now, a function that executes on a GPU is called a kernel. Another important thing to note is that all data required by the kernel has to be present in the global memory for it to proceed. And this entails transferring data from CPU's RAM to GPU. Since this is a really slow operation, we need to ensure that we do a large number of computations after every memory transfer so that the cost of moving data is amortized over these computations. Now let's understand how a GPU kernel gets executed. We call the CPU the host and the GPU the device. The host code calls the GPU kernels whenever required. A kernel executes as a grid of blocks. A block has a fixed number of threads, and we can synchronize the threads of a single block. It also supports atomic instructions to avoid race conditions. And lastly, it also provides the facility of nested kernels where we can launch a kernel from another kernel. Having understood the GPU and kernel architecture, we now observe that in our implementation, the data is transferred to the GPU before loop 2 and is brought back to the CPU after loop 2. Loop 2 executes as a single-threaded kernel inside GPU, and we leverage the nested kernels facility by launching individual kernels for operations inside the serially executing loop 2. Note that by doing this, we ensure that the number of computations between successive data movements is sufficiently large. Now let's understand one of the kernels that we've implemented for distilling cubes based on flags. So let's say you have this input array in which the elements with a tick mark need to be distilled in. For this, we launch two blocks with 4 threads in each block. One of the 4 threads is the reader thread. By leveraging atomic instructions and shared memory, every thread calculates the local indices at which the distilled element will be written if distilled. Apart from this, the leader thread also calculates the global start index from where the distilled elements of the corresponding block will be written in the output array. Finally, when we add the global index of the leader thread and the local index for individual thread, we get the position at which each distilled element should be written, and it eventually gets written. Notice that by having multiple blocks of threads, we ensure that the only threads in a single block contain in atomic updates for the index calculations. Next, let's look at the kernel that determines for every cube of the onset whether a given cube C can be expanded to feasibly cover it. So let's say we have the onset and the offset both of size 8, and hence there are 8 cross 8 distance calculations that need to be done. Now we divide these 8 cross 8 computations into 4 grids of size 4 cross 4. Each grid consists of 4 thread blocks, and each block has a 2 cross 2 tile. In a tile, the threads of a first row and first column load the data into the shared memory, then it uses that data in the shared memory to do the computations. Moreover, we only launch one grid of threads from GPU, and each thread processes one distance value in each grid shown by the color-coded threads. This ensures that the cost of launching a thread is amortized over 4 computations. This is necessary here since the size of the onset and the offset can be hundreds of thousands, and hence the full matrix can be of the order of billions. Note that we implemented other kernels using similar ideas, and we encourage you to check out our paper for the details on them. Now let's discuss the experiments. For that, we had 3 classes of PLAs: small, medium, and large, containing the specified number of minterms. There were 10 PLAs for each class, and they were extracted from the NeulaNet pipeline. We did our experiments on the NVIDIA GeForce GTX 1080 GPU. We measured the runtime of Espresso-2 and Espresso-GPU for finishing a single expand step, and we observed that Espresso-GPU runs more than 100 times faster than Espresso-2. Also note that the speedup consistently increases with the size of the PLA. This indicates that our implementation scales nicely with the size of the PLA. Notice that the PLAs with hundreds of thousands of minterms took 4 hours on CPU and just take 12 minutes on GPU. Thank you.